step outside on a clear night and look upward. The sky seems to present itself all at once. The moon hangs above the horizon. Stars occupy their familiar patterns. Perhaps a planet shines between them, while beyond the reach of your eyes, distant galaxies fill the darkness. Everything appears to belong to one enormous scene, a single universe existing around you at this moment. But that is not what you are seeing. The moon you see is already slightly old. Its light takes a little more than a second to cross the space between its surface and your eyes. The sun is farther away, so daylight reaches Earth about 8 minutes after leaving it. If the sun could somehow change without warning, Earth would continue receiving its earlier light until those minutes had passed. The delay grows rapidly beyond the solar system. The nearest star system appears to us as it was more than 4 years ago. Light from stars across the Milky Way may have been traveling for hundreds, thousands, or tens of thousands of years. When we observe another large galaxy, we may be seeing light that began its journey before human civilization existed. The most distant galaxies appear not as they are today, but as they were billions of years ago, when the universe itself was younger. These images are not false. The photons entering a telescope carry real information about real events. They can reveal the temperature of a star, the motion of a galaxy, the elements inside a cloud of gas, or the violence of an explosion. Astronomy works because old light remains physical evidence. Yet the evidence does not arrive from one shared moment. Every direction in the sky contains a different depth of time. Nearby objects appear relatively recent. Distant objects appear increasingly ancient. A single astronomical image may therefore look like a map of space, while also being a collection of moments that never happened together. The sky is not one cosmic landscape photographed in the present. It is an archive whose pages arrive at the same observer from different ages. Better telescopes can collect fainter light. They can sharpen details, separate wavelengths, and detect objects far beyond unaided vision. But no improvement in mirrors, sensors, computers, or engineering can make a signal reach us before it has crossed the distance in between. Even a perfect telescope would still receive the past. This creates a deeper problem than ordinary delay. If we know how far away an object is, perhaps we can estimate what it might be doing now. We can measure its motion, model its evolution, and project its history forward. But a prediction is not an observation. During the unseen interval, a star may change, a galaxy may collide, or an event may occur whose signal has not had time to arrive. A model can offer the best supported reconstruction, but it cannot turn missing information into witnessed fact. And the problem becomes more difficult when we stop thinking about individual stars and ask about the universe as a whole. To observe everything as it really is, we would need more than perfect eyesight. We would need information from every region at one common cosmic moment. We would need a universal version of now, and some way for all of its signals to reach a single observer together. Physics does not provide such a view. The obstacle is not simply that the universe is large, nor that our technology remains primitive. The obstacle is built into the way information moves, the way time is measured across distance, and the way space itself has evolved. Some regions can be seen only in their past. Some have never been able to send us any signal. Others may remain visible through ancient light even though their present can never reach us. So the question is not merely how far our telescopes can see. It is whether any observer, anywhere, could ever assemble a complete and simultaneous portrait of the cosmos. To answer that, We must begin with the rule already hidden in the night sky. Distance is not only separation. In astronomy, distance is also time, and every view is shaped by both. Once distance becomes time, the universe begins to look less like a place spread around us and more like a history arranged by depth. Every additional kilometer creates a slightly longer delay. Across ordinary human distances, that delay is too small to notice. Across astronomical distances, it becomes the organizing principle of everything we can observe. Light travels through empty space at about 300,000 kilometers each second. Yet space is larger still. Even light needs more than a second to reach us from the moon, minutes to cross the distance from the sun, and hours to travel between the outer planets and Earth. This is why astronomers use the light year. Despite its name, a light year is not a measure of time. It is the distance light travels through a vacuum during 1 year. Saying that a star is 10 light years away also tells us something immediate about observation. The light reaching us tonight began its journey 10 years ago. That connection produces a ladder of delay. We see the sun as it was roughly 8 minutes earlier. We see Sirius as it was more than 8 years ago. Some bright stars in our sky are hundreds or thousands of light years away, so their visible light began traveling long before anyone now alive was born. The center of the Milky Way appears through signals that have crossed space for roughly 26,000 years. The Andromeda Galaxy is seen through light that has traveled for about 2.5 million years. A galaxy 100 million light-years away is presented to us as it existed when very different forms of life occupied Earth. At billions of light-years, we encounter galaxies during earlier stages of their development. Their shapes, stars, and surrounding environments reveal conditions from a younger universe. The result is strange but precise. Looking farther does not merely show us more space, it shows us earlier time. A telescope is therefore not a window onto a universal present. It is closer to an instrument for collecting messages that began their journeys at different dates. A sensitive detector can recover signals that are extraordinarily faint. Spectrographs can separate light into wavelengths and reveal motion, temperature, chemical composition, and magnetic conditions. None of these abilities cancels travel time. They improve what we learn from an arriving signal, not when that signal arrives. Nor can another known messenger provide instant access. Radio waves, infrared light, visible light, ultraviolet radiation, X-rays, and gamma rays are all forms of electromagnetic radiation. In a vacuum, they propagate at the same fundamental speed. Gravitational waves also travel at light speed according to general relativity, a prediction supported when gravitational and electromagnetic signals from the same distant event arrived in close agreement after crossing immense distances. Material messengers are slower. Neutrinos travel extremely close to light speed when their energies are high, but because they possess mass, they do not exceed it. Spacecraft, dust grains, atoms, and any physical probe move far more slowly. Changing the kind of detector can reveal different features of an event, but it does not create a courier capable of delivering distant news instantaneously. Suppose, however, that we know the distance to a star, its velocity, its mass, and its stage of evolution. Could we calculate forward from the old light and determine its present condition? We can certainly estimate. Astronomy constantly uses physical models to reconstruct processes that cannot be watched from beginning to end. A model may show that a star is likely still shining, that a galaxy will continue forming stars, or that two objects are moving toward a future encounter. These are meaningful scientific inferences, often supported by several independent observations. But an estimate of the present is not a measurement of the present. The difference matters because prediction depends on available information and on the reliability of the model. If a distant star underwent an unexpected eruption after the light we currently see departed, that information is still crossing space. We cannot detect the event until its signal arrives. We might calculate probabilities, but we cannot honestly claim to have observed what remains outside our causal reach. Imagine watching a recorded image of a ship crossing a distant ocean. If you know the recording is 1 day old, its speed and direction may help you estimate where the ship is now. Yet storms, mechanical failures, or course changes could make the estimate wrong. Better mathematics can improve the prediction, but it cannot convert tomorrow's missing report into today's direct evidence. The astronomical problem is deeper because the delays are not days. They can span the entire rise of civilizations, the evolution of species, the formation of planets, or most of cosmic history. The farther away the source, the longer the unobserved interval between the state we measure and the state we wish to call current. This also means there is no master observer receiving every cosmic event at once. An astronomer in another galaxy would occupy a different location and would collect a different set of signals. That observer might see events whose light has not reached Earth, while remaining unable to see events already visible to us. Each location receives its own historical record, shaped by the paths that information has had time to travel. The limit is therefore not peculiar to humanity, Earth, or our instruments. It belongs to observation itself. Any observer must build knowledge from signals arriving at a particular place and moment. Every detector waits for causes to produce effects. Every image of distance is also an image of delay. Yet one possibility still seems open. Perhaps all observers are looking at different historical records, but those records could be translated onto a single shared timeline. If every delay were known, perhaps every old image could be projected forward toward one universal present. Before that idea can work, physics must answer a deceptively simple question. When two events happen far apart, what does it mean to say they are happening now? At first, the question seems almost too simple to cause trouble. We use the word now constantly. The clock beside you shows a time. Another clock across the room can be synchronized with it. If both display the same number, we say they mark the same present moment. It feels natural to extend that idea outward, from one room to a city, from Earth to the planets, and eventually across the universe. For nearby places, moving together at ordinary speeds, this works extremely well. Nothing in daily experience warns us that a universal present might be difficult to define. The difficulty appears when observers move differently and the distances between events become large. Einstein's theory of special relativity showed that measurements of space and time depend on the motion of the observer. This does not mean that every statement is a matter of opinion. A clock still records a definite amount of time along its own path. An event that causes another event remains earlier than its effect for every observer who can describe that causal connection. But events separated so widely that no light signal could travel from one to the other in time present a different case. They are called space-like separated. Because neither event can cause the other, different observers moving relative to one another can disagree about which happened first. One observer may judge the events simultaneous. Another may place one before the other. To see why, imagine two flashes occurring at opposite ends of a long-moving spacecraft. An observer standing halfway along the ship may receive the two flashes together and, after accounting for equal distances, conclude that they occurred at the same time in the ship's frame. An observer watching the spacecraft pass from outside is moving differently relative to the flashes. In that observer's frame, the ship moves toward one flash and away from the other, and the timing assigned to the two events is not the same. What counts as simultaneous across a distance is not fixed independently of the observer's state of motion. This is the relativity of simultaneity. It does not say the flashes are imaginary. It does not say reality depends on whether someone looks at it. Both flashes are real events in space-time. What relativity removes is the assumption that the entire universe can be divided into one uniquely correct set of events, all sharing the same now. For events connected by a possible signal, causal order remains secure. If one star explodes and its radiation later strikes a detector, every valid observer agrees that the explosion came before the detection. No change of perspective can place the received signal before its source. Relativity protects cause and effect, even while allowing disagreement about the order of distant events that cannot influence one another. This distinction matters because the cosmic snapshot we imagined requires more than collecting delayed light. It requires selecting one state from every distant region and declaring that all those states coexist at the same present moment. Relativity allows physicists to choose such slices for calculation, but it does not provide a single observer-independent slice that nature labels as the universal present. Cosmology, nevertheless, speaks meaningfully about the age of the universe and about conditions at particular cosmic times. This is possible because the standard cosmological model describes the large-scale universe as approximately homogeneous and isotropic. On sufficiently large scales, matter is treated as a smooth cosmic distribution, even though smaller scales contain galaxies, clusters, stars, planets, and enormous empty regions. Within that model, physicists imagine observers moving with the average cosmic expansion. Such observers are called co-moving observers. Each sees the large-scale matter around them as following the general Hubble flow, rather than possessing a large motion relative to it. Clocks carried by this ideal family of observers define cosmic time. A surface of constant cosmic time is then a useful theoretical construction. It allows cosmologists to say what the model predicts across space when the universe has reached a certain age. Statements about the early universe being hotter and denser, or about structures growing over billions of years, use this shared cosmological clock. This cosmic time is not arbitrary. It is tied to the symmetries of the expanding model and is constrained by observations. Measurements of the cosmic microwave background, galaxy distributions, and expansion history can be combined to estimate the time elapsed since the early hot phase. Within the standard model, that age is about 13.8 billion years. Yet a useful coordinate is not the same as a directly visible universal moment. A constant cosmic time surface may represent what the model assigns to distant regions at one stage of expansion, but no telescope receives light from every point on that surface simultaneously. The farther a region lies from us, the earlier the cosmic time represented by the light now arriving from it. We can use equations to infer how a distant region may have evolved after emitting the signal we detect. These methods can produce reliable scientific knowledge. But the reconstructed state remains an inference within a tested framework. It is not a photograph delivered from that distant region's assigned present. There is another reason for caution. The large-scale smoothness used to define cosmic time is an approximation. The real universe contains gravitationally bound systems, local motions, curved space-time around massive objects, and regions with different densities. Cosmic time remains useful for describing the average expansion, but it should not be mistaken for an absolute clock ticking identically in every physical circumstance. The question, what is happening everywhere now, therefore contains two separate problems. First, distant simultaneity requires a chosen frame or cosmological slicing. Second, even after that choice is made, information from the selected distant events must still reach an observer. The first is a problem of how space-time defines time across separation. The second is a problem of causal access. Choosing cosmic time can organize a theoretical portrait, but it cannot make that portrait observable all at once. An observer receives only those events capable of sending signals to the observer's location by the moment of measurement. Everything else lies outside the available record, regardless of how clearly the model assigns it a coordinate time. Physics therefore replaces the idea of a universal live image with something more precise. Instead of asking which events exist everywhere on one absolute present, it asks which events can influence us here and now. The answer has a definite geometric shape. It is built from every path that light could have taken to reach this moment, and it is known as our past light cone. To understand a past light cone, begin by reducing observation to its simplest form. A telescope may be enormous. Its mirrors may collect light for hours, and its instruments may separate that light into thousands of wavelengths. But every measurement ultimately occurs at a particular place and at a particular moment. A photon reaches a detector here. A gravitational wave disturbs an instrument now. Observation always ends at an event in spacetime. From that event, imagine tracing every arriving ray of light backward. One ray may lead to the moon a little more than a second earlier. Another may lead to the sun roughly 8 minutes earlier. Others lead to stars, years or centuries in the past, and still others to galaxies whose light began traveling billions of years ago. Together, all possible light paths form the surface of a geometric structure called the past light cone. The word cone comes from the way this structure is drawn on a space-time diagram. Time is shown vertically, while space is simplified along the horizontal direction. At the observer's present event, the cone narrows to a point. Moving backward in time, the region from which light could have arrived becomes wider. The farther into the past we go, the farther away a possible source could have been, while still sending a signal that reaches us now. The diagram is simplified, but the causal meaning is exact. Events on the surface of the cone can be connected to us by a light speed signal. Events inside the cone could have influenced us through light or through something moving more slowly, provided the signal began early enough. Events outside the cone are too widely separated from our present event for any known influence to have reached us yet. Those outside events are not necessarily unreal, empty, or unimportant. They are simply outside our present causal past. Something may be happening there according to a chosen coordinate system, but until a signal completes the journey, it cannot become part of our direct evidence. This gives observation a boundary more fundamental than the power of an instrument. A larger telescope can detect weaker signals within causal reach. It cannot pull an event from outside the past light cone into the observable record. The limitation remains even if the telescope is perfect, because the missing information has not arrived at its location. The cone also explains why the sky contains different times without treating those times as a random collection. Every visible event occupies a definite place on our causal past. Nearby events lie close to the cone's tip and are seen relatively recently. Distant events lie deeper along its surface and are seen at earlier stages. The night sky is therefore organized by the geometry of information. The phrase past light cone can sound as though it describes only visible light. In fact, it represents the maximum causal boundary for every kind of information. Radio signals, X-rays, gravitational waves, and any slower messenger must all respect the same geometry. It is important to distinguish the surface of the cone from its interior. Light itself follows paths along the surface. A slower object or signal follows a path inside it. Earth, for example, moves through time along a path that remains inside its own future light cone. Any cause that reaches us through an ordinary material process must originate within the region permitted by this causal structure. Events outside the cone are described as space-like, separated from our present event. No signal moving at or below light speed can connect them to us by now. This is the same separation that allowed distant observers in the previous section to disagree about event order. Where causal contact is impossible, no observer-independent sequence is forced between the events. Where causal contact exists, cause must remain before effect. The past light cone is not unique to Earth. Place an observer on a planet in the Andromeda galaxy, and that observer has a different cone. It overlaps with ours in some regions, but includes events we cannot yet see, and excludes some events already available to us. Move the observer to another galaxy, another era, or another state of motion, and the accessible record changes again. No observer's cone is automatically more real than another. Each is centered not on a privileged location in the universe, but on the event where that observer receives information. Earth appears at the center of our observable view for the same reason that every person appears at the center of their own visual horizon. It is a consequence of where observation occurs, not evidence that the cosmos was built around us. Could many observers combine their records and create the missing universal picture? They could certainly share information after signals pass between them. A network spread across space would sample more locations than a single detector. But combining observations does not defeat causality. The records must travel to a common receiver before they can be compared. By the time they arrive, they describe different earlier events, and the shared result still belongs to the receiver's past light cone. There is no place outside spacetime where all cones can be viewed directly at once. A theoretical diagram may represent many observers and many events, but the diagram is a model assembled from measurements and physical laws. It is not itself an observation made from beyond the universe. This distinction between a model and an observer's accessible past is central to cosmology. Scientists reconstruct an enormous four-dimensional history from the signals inside our cone. They infer how stars evolved, how galaxies assembled, how matter clustered, and how the cosmic expansion changed. The success of those reconstructions can be tested because different observations must agree with one another. Yet every test still uses information that has reached us. A correct theory can describe events outside our current cone, just as a weather model can describe conditions beyond a station's horizon. But the description remains an extrapolation until evidence arrives, and some evidence may never arrive at all. So far, the cone might seem simple to calculate. If light travels at a fixed speed and the universe has existed for a finite time, perhaps the greatest observable distance should equal the speed of light multiplied by the age of the universe. With an age of about 13.8 billion years, the obvious expectation would be a radius of 13.8 billion light-years. But that is not the distance cosmologists infer. Within the standard cosmological model, the present co-moving radius of the observable universe is roughly 46 billion light-years. Its diameter is therefore close to 93 billion light-years. No photon traveled for 46 billion years, because the universe is not that old. Nothing locally broke the speed limit. The apparent contradiction arises because the simple cone imagined in a static spacetime is not the cone of our actual universe. While ancient light traveled, the large-scale distance between regions changed. The geometry through which the photon moved was evolving. This means that three statements can all be true. The universe can be about 13.8 billion years old. Light can always move locally at its fixed speed. And matter whose ancient light reaches us today can now be roughly 46 billion light-years away in present co-moving distance. To understand how those statements fit together, the light cone must be placed inside an expanding cosmos. We must stop imagining a photon crossing a fixed stage and follow it through space, whose scale changes throughout the journey. 1,450 narration words. A photon crossing a room moves through a distance that remains effectively fixed. The walls do not separate noticeably while the light is traveling, so its journey can be described with the familiar rule: distance equals speed multiplied by time. Across the universe, that simple picture is incomplete. The photon still moves locally at the speed of light, but the large-scale geometry connecting its source and destination changes during the journey. Cosmic expansion does not mean that galaxies are all flying away from one central explosion through a pre-existing emptiness. On the largest scales, the Standard Model describes the distances between freely moving regions as increasing with time. There is no central point from which expansion began, and no outer direction into which the universe must expand. Every sufficiently distant observer following the average cosmic flow sees other remote regions separating in the same general pattern. Cosmologists describe this changing scale with a quantity called the scale factor. It is a way of comparing cosmic distances at different times. By convention, the scale factor today is often assigned the value 1. At earlier times it was smaller, meaning the average separation between co-moving locations was smaller than it is now. A co-moving location acts like a label attached to the expanding cosmic pattern. A galaxy following the average Hubble flow can remain near the same co-moving coordinate even while its proper distance from another galaxy increases. This distinction lets cosmologists discuss two different ideas without confusing them. Proper distance asks how much spatial separation the model assigns between locations at a chosen cosmic time. Co-moving distance removes the changing scale factor, allowing the locations to be compared using a grid that expands with the universe. Neither description is a trick. They answer different questions. If we ask how far apart two co-moving galaxies would be measured on a constant cosmic time slice today, we want a present proper distance. In the common normalization used by cosmologists, that present proper distance has the same numerical value as co-moving distance. If we ask how separated they were when ancient light was emitted, the proper distance was smaller. Now place a photon in this evolving geometry. At every point along its route, a nearby observer measures it moving at c. Expansion never causes the photon to crawl locally, and the photon never exceeds the local speed limit. But the proper distance between the photon and its destination can behave in ways that would be impossible on a static stage. Imagine walking toward a destination while the ground between you and the destination stretches. Your local walking speed can remain constant, even though the total remaining distance changes for another reason. It fails if taken too literally. Cosmic space is not a sheet made of material. Galaxies are not glued to rubber, and local bound systems do not simply stretch with the average expansion. Atoms, people, planets, solar systems, and galaxies are held together by forces or gravity. The expansion described by cosmology becomes important across sufficiently large, unbound distances. It is a statement about the average geometry of the universe, not a force steadily enlarging every object. As the photon travels, the expansion also changes its wavelength. A wave emitted when the cosmic scale factor was smaller arrives with a longer wavelength. This cosmological redshift gives astronomers a record of how much the scale changed between emission and observation. A redshift of 1, for example, corresponds in the simplest cosmological interpretation to wavelengths stretched to twice their emitted value, while the scale factor has doubled since emission. Astronomers identify familiar patterns produced by atoms and compare the observed wavelengths with those measured in laboratories. Turning that shift into an age, travel time, or distance requires a cosmological model describing how expansion changed throughout the journey. This is one reason a distant galaxy can have several distance values, each scientifically correct within its definition. Lookback time describes how long the detected light has been traveling. Present co-moving distance describes how far away the source's co-moving location is assigned to be now. Luminosity distance relates its observed brightness to its intrinsic power while accounting for expansion. Angular diameter distance relates an object's apparent size to its physical size at emission. A statement such as, "This galaxy is 10 billion light-years away," is incomplete unless we know which distance is intended. At modest distances, the differences may be manageable. At extreme redshifts, they become essential. Consider a galaxy whose light has traveled for more than 10 billion years. When that light began its journey, the galaxy was not located at the same proper distance that cosmologists assign to its co-moving position today. During the photon's flight, the scale factor increased. The galaxy's present inferred separation can therefore be much greater than the simple travel time expressed in light-years. This does not mean the photon secretly traveled faster than light. It means how long the light traveled and how far away the source is now refer to two different measurements in an evolving spacetime. Confusing them creates the apparent contradiction. The same logic explains cosmological redshift more accurately than the image of an ordinary object racing through static space. A galaxy can also possess a local motion relative to the average cosmic flow, producing an additional Doppler contribution. But at large scales, much of the observed redshift is interpreted through the change in the cosmic scale factor between emission and reception. To reconstruct the photon's history, cosmologists use observations to constrain the expansion rate at different epochs. The rate has not remained constant. Radiation dominated the dynamics of the very early universe. Matter later became more important, and accelerated expansion associated with dark energy dominates the recent large-scale behavior in the Standard Model. The exact journey, therefore, depends on the full expansion history. Scientists integrate the photon's path through that history rather than multiplying the present expansion rate by time. Measurements from the cosmic microwave background, exploding stars, galaxy clustering, and characteristic distance patterns provide overlapping constraints on the model. The resulting distances are inferred, not measured by placing a ruler between Earth and a remote galaxy. Yet inference does not make them arbitrary. A successful cosmological model must explain many independent observations with one consistent expansion history. If its predicted brightnesses, angular scales, redshifts, and cosmic ages disagree with the data, the model must be changed or rejected. Still, Every inferred distance carries assumptions. The standard values usually quoted for the observable universe depend on the framework known as the lambda cold dark matter model. It assumes general relativity on cosmic scales, a large-scale homogeneous and isotropic geometry, cold dark matter, and a dark energy component behaving like a cosmological constant. Current evidence supports this framework remarkably well, but model dependence must remain visible in the narration. A calculated present distance is not a direct photograph of a ruler laid across the cosmos. It is the distance that best fits observations under a tested geometric and physical description. Expansion also prevents a common misunderstanding about the Big Bang. If all co-moving separations were smaller in the past, it may be tempting to imagine matter exploding outward from one point into empty surroundings. But in the standard picture, the early hot, dense condition occurred throughout the region that became our observable universe. Running the expansion backward reduces distances between co-moving locations everywhere. It does not identify a central launch site inside space. This is why every distant observer can see an approximately isotropic expansion centered on their own location. The pattern does not make each galaxy the true center. It reflects the absence of a preferred center within the homogeneous model, much as every point on an ideal expanding coordinate grid sees other distant points recede. The changing scale now provides the key to the numerical puzzle. The oldest light reaching us did not begin its journey from a location already separated from us by 46 billion light-years. The relevant regions were much closer in proper distance when their photons started traveling. While the photons moved toward the location that would become Earth, expansion increased the present separation assigned between our co-moving position and theirs. Thus, the age of the universe limits how long light has traveled, while the integrated expansion history determines the present co-moving distance to the source. One quantity is a duration along the photon's journey. The other is a model-defined separation on today's cosmic slice. With that distinction in place, the apparently impossible scale of the observable universe can finally be understood. A cosmos about 13.8 billion years old can contain an observable region whose present co-moving radius is roughly 46 billion light-years, without any photon outrunning light and without placing Earth at the center of creation. The two numbers now stand beside each other without contradiction, but their meaning deserves to be followed carefully. According to the standard cosmological model constrained by observations from the Planck mission and other measurements, the universe is about 13.8 billion years old. Yet the present co-moving radius of the observable universe is roughly 46 billion light-years. If space had remained static, the mismatch would be impossible. Light traveling for no more than 13.8 billion years could cross no more than 13.8 billion light-years. But the light arriving from the earliest visible regions did not cross a distance that stayed fixed. It crossed an evolving cosmos. Imagine a very ancient photon beginning its journey toward the matter that would eventually form our galaxy. At the moment of emission, the proper separation between the photon's source and our co-moving location was far smaller than the distance assigned between those locations today. The photon moved locally toward us at the speed of light. Meanwhile, the cosmic scale factor increased, changing the proper distances between widely separated co-moving positions. The photon did not need to cross today's entire 46 billion light-year separation. That number describes where the source's co-moving position is inferred to be on a present cosmic time slice. It is not the length of the path measured by simply multiplying the photon's travel duration by its local speed. During the early stages of its journey, expansion could increase the proper separation between the photon and us, even while the photon moved locally in our direction. Later, as the expansion rate evolved, the photon made net progress across the changing geometry and eventually arrived. Its entire route is calculated by integrating light propagation through the expansion history. The age of the universe tells us the maximum available cosmic duration since the early hot phase. The particle horizon distance asks a different question. After accounting for the scale factor at every stage, what is the present co-moving distance to the most remote regions from which a signal could have reached us? Within the standard model, that calculation produces a radius near 46 billion light-years. Doubling the radius gives an observable diameter close to 92 or 93 billion light-years. The wording matters. This is the diameter of the observable universe in present co-moving coordinates. It is not the distance a single photon traveled, and it is not a measurement of the entire universe. The observable sphere contains the regions whose past signals can reach our location by now. Its boundary depends on our position and on cosmic history. An observer in a galaxy billions of light-years away would possess a different observable sphere centered on that observer. Much of it could overlap with ours, but some regions would differ. This does not place Earth at the true center. Any observer sees incoming signals arranged around the place where they are received. The symmetry is observational and geometric, not evidence of a privileged cosmic location. The comparison with an explosion can be especially misleading here. In an ordinary explosion, debris moves away from a central point through surrounding space. An observer could, in principle, identify the center by tracing the debris backward. In the standard cosmological picture, expansion is a change in large-scale spatial relationships. Every sufficiently large region was denser in the past. There is no known point inside the observable universe from which all galaxies were launched. The Big Bang therefore did not happen at a location 46 billion light-years away. The early hot condition occurred throughout the region that developed into everything we can observe. Wherever an observer exists today, looking far enough in every direction means looking toward earlier cosmic conditions. This is why the oldest observable light surrounds us as a background rather than appearing in one direction. It does not mark a distant explosion center. It marks events on our past light cone from an epoch when the universe became transparent. The 46 billion light-year value also requires another qualification. The matter associated with the most ancient electromagnetic light is not seen at its present state. We see the photons released when the universe was only about 380,000 years old. The present co-moving distance tells us where that matter's co-moving position is assigned today by the model, not what we directly observe happening there now. Those regions may have evolved into structures over billions of years, but their later light has not all reached us. The farthest light gives us a younger version of their history. Once again, a present model distance does not provide a present photograph. The scale becomes even more surprising when we consider what observable does not guarantee. A source can be observable because light emitted long ago is reaching us now, while its present condition is already beyond any signal we will ever receive. Visibility concerns the past path of light. Reachability and future communication concern a different boundary. This distinction prevents another common mistake. We cannot assume that every galaxy visible today could receive a message sent from Earth now. Nor can we assume that waiting longer will eventually show us the current state of every visible source. The future expansion of space changes which new signals can ever arrive. For the moment, however, the important result is that no local speed limit has been broken. Every photon is measured locally at c. The large radius appears because present co-moving distance incorporates how the cosmic scale changed during billions of years of travel. A useful way to keep the quantities separate is to ask three questions. First, when was the light emitted? Second, how long has it been traveling? Third, what present distance does the cosmological model assign to the source's co-moving location? At nearby scales, the answers may appear almost interchangeable. Across most of cosmic history, they are not. Suppose an ancient photon has traveled for nearly the age of the universe. Its source did not remain at one fixed distance during that time. The expansion history transformed the relationship between the original separation, the photon's route, and the distance assigned today. There is therefore no reason for the travel time in years to equal the present co-moving distance in light years. The numerical result is based on a measured and fitted expansion model. Parameters such as the present expansion rate, matter density, radiation content, spatial curvature, and dark energy behavior determine the calculation. Small revisions to those parameters slightly change the exact horizon distance. This is why responsible narration uses approximate language rather than presenting 46 billion light-years as an infinitely precise observed boundary. Even with that qualification, the central conclusion is robust within the standard model. The observable universe is far larger in present co-moving extent than a static space calculation based on age alone would suggest. And the full universe could be larger still. The observable radius marks only the reach of past causal contact. Space may extend far beyond our horizon. It may be finite, with a global shape much larger than the visible region, or it may be spatially infinite. Current observations can constrain curvature and search for repeating patterns, but they have not determined the total size. Therefore, doubling 46 billion light-years gives the span of our observable region, not a cosmic outer diameter. Beyond that boundary, there may be more galaxies, more matter, and more space whose signals have not reached us. Their absence from our sky is not evidence that they do not exist. The scale shock is not that the universe somehow allowed light to cheat. It is that our familiar equation assumed a fixed stage, while cosmic history changed the stage throughout the journey. Once the correct geometry is used, the age, the speed of light, and the observable radius agree. Yet this resolution opens a more unsettling question. If distant separations can grow through cosmic expansion, their rate of increase can exceed the speed of light. Standard calculations indicate that many galaxies we observe are receding from us faster than c in the cosmological sense. How can their light reach us at all? Answering that requires one separation between local motion through space and the changing distance created by cosmic expansion. The phrase "faster than light" immediately sounds like a violation of relativity. According to special relativity, no material object can pass a nearby observer at a speed greater than light in a vacuum. No local experiment allows a spacecraft, particle, or message to overtake a light beam beside it. That restriction remains intact throughout cosmology. Yet cosmologists can still say that a distant galaxy is receding from us faster than light. The reason is that cosmological recession is not the same quantity as local motion measured in one small region of spacetime. It describes how a model-defined proper distance between widely separated co-moving locations changes with cosmic time. Across a small enough region, spacetime can be treated as approximately flat. A local observer measures light moving at c and any massive object moving below c. Across billions of light-years, however, one cannot combine all local measurements, as though the universe were one rigid, static coordinate system. The geometry between the endpoints evolves. The recession rate assigned to a sufficiently distant galaxy follows the large-scale expansion. The farther away a co-moving galaxy lies, the more expanding space exists between its location and ours. At great enough distances, the total proper separation can increase by more than 1 light-year during 1 year of cosmic time. This rate can exceed c without any galaxy locally racing past a neighboring photon. That distinction is subtle because both quantities are described with the word speed. One is a local velocity through a nearby inertial frame. The other is a rate of change of a long cosmological distance. Special relativity directly limits the first. It does not require the second to remain below c. But if the distance between us and a galaxy is increasing faster than light can cross distance locally, how can photons from that galaxy ever arrive? The answer depends on how expansion changes while the photon travels. Imagine a photon emitted toward us from a region whose proper distance is initially increasing. The photon always moves locally in our direction at c. Nevertheless, the expanding geometry between the photon and us can initially add distance faster than the photon removes it. In proper distance terms, the photon may begin its journey while becoming farther away. That sounds fatal, but the boundary at which recession equals c is not necessarily fixed. It is called the Hubble sphere. Its distance depends on the Hubble parameter, which changes over cosmic history. As the expansion rate evolves, the Hubble sphere can change, and a photon that was once outside it can later find itself inside. Once conditions allow its proper distance from us to decrease, the photon begins making net progress and may eventually arrive. We can therefore receive light emitted by matter whose recession rate at the time of emission, or even today under a chosen distance definition, exceeds c. This is not merely a theoretical curiosity. In the standard cosmological model, galaxies at sufficiently high redshift are assigned superluminal recession rates, yet they are observed. Their photons reach our telescopes because observability depends on the entire history of the light path, not on a single comparison between recession rate and c at one moment. The Hubble sphere is therefore not generally an absolute wall. It marks the distance where the recession rate at a chosen cosmic time equals the speed of light. It does not automatically separate everything visible from everything invisible. Photons can cross this changing boundary as the expansion history evolves. Confusing the Hubble sphere with a true horizon creates several errors. It suggests that anything beyond it can never be seen, even though we already observe objects that were beyond it. It also suggests that crossing it makes a galaxy disappear immediately. In reality, the light already emitted continues along its causal path, and what reaches us depends on the whole geometry. To understand what is truly observable, 3 boundaries must be kept separate. The first is the Hubble sphere. It answers a present geometric question. At what proper distance does the cosmological recession rate equal c at this cosmic time? Its location changes as the Hubble parameter changes. The second is the particle horizon. It answers a question about the past. What is the greatest present co-moving distance from which any signal could have reached us since the early universe? This boundary defines the outer limit of our past causal contact and gives the approximate 46 billion light-year observable radius. The third is the cosmological event horizon. It answers a question about the future. From which present events can a signal ever reach us, even if we wait indefinitely? Its existence and location depend on the future expansion history. That difference will become essential when the story turns from ancient visibility toward future isolation. These boundaries can occupy different distances because they describe different things. The Hubble sphere concerns an instantaneous recession rate. The particle horizon concerns all signal travel available in the past. The event horizon concerns all signal travel remaining in the future. A galaxy can therefore lie beyond the Hubble sphere and still be visible. Its ancient photons may already be traveling along paths that eventually enter our region. A galaxy can also be visible today, while its present events lie beyond our event horizon. We receive its old light, yet light emitted there now may never reach us. This separation between seen and reachable is one of the most counterintuitive consequences of an expanding universe. Seeing an object does not mean we have access to its current state. It does not guarantee that a message sent today can reach it, or that a reply can return. Visibility is a record of past causal contact, not proof of future communication. There is also no single moment when a galaxy appears to freeze at a visible wall. As its newly emitted light becomes unable to reach us, older light already on the way may continue arriving for an immense time. The galaxy becomes increasingly redshifted and faint. Its observed evolution can appear slowed and stretched, while the source itself continues along its own local history. The language of recession requires care for another reason. At cosmological distances, velocity depends on the chosen definition of distance and time. Saying that a galaxy recedes faster than light is meaningful within the standard FLRB description using proper distance and cosmic time. It should not be treated as a local speed measured by one observer standing beside the galaxy. This is why no experiment in the distant galaxy would detect itself breaking relativity. A local observer there sees nearby light travel at c and nearby matter move below it. That observer may assign our galaxy a large recession rate using the same cosmological model, just as we do for theirs. Every observer following the large-scale flow can describe themselves as locally at rest, while remote co-moving distances increase. The symmetry again shows that expansion has no ordinary center. Superluminal recession is a property of the evolving relationship across vast spacetime, not a rocket-like motion away from Earth. Once these distinctions are made, the apparent paradox dissolves. Light never loses its local speed. Distant proper distances can still grow faster than c. A changing Hubble sphere can be crossed by photons. Past visibility and future reachability are governed by different horizons. The scientific lesson is broader than the speed question. Words such as distance, velocity, horizon, and now have familiar meanings in ordinary life, but cosmology forces each one to be defined operationally. Many cosmic paradoxes arise when a definition suited to static, local space is extended across an evolving universe. We can now identify the boundary relevant to what has ever been observable. It is not the place where recession happens to equal c today. It is not the point where galaxies physically end. It is the particle horizon, the limit set by the finite age of the universe, and the total expansion history through which signals have traveled. Everything inside that boundary is not necessarily visible with current instruments, but it has at least been within possible causal contact under the model. Events beyond it have not had enough cosmic history for any signal to reach us. That does not mean nothing lies there. It means our past light cone has not reached it. The edge of the observable universe is therefore not an edge of existence. It is the edge of received information. The edge of received information is easy to imagine as a distant shell, perhaps the final surface of space itself. But the particle horizon is not a wall made of matter, and it is not a border where the universe ends. It is a boundary in causal history. Its defining question is precise. What is the greatest present co-moving distance from which a signal could have reached this observer since the beginning of the expanding cosmic history described by the model? The answer depends on more than the age of the universe. It depends on how the scale factor changed throughout that age. Cosmologists calculate the total distance light could cover in co-moving coordinates by integrating its journey through the expansion history. For our location today, under standard cosmological parameters, the result is roughly 46 billion light-years. This boundary is called a particle horizon because it marks the maximum reach of past causal influence carried by particles or signals. An event beyond it has not had enough cosmic time, given the evolving geometry, to affect us. No light, gravitational wave, neutrino, spacecraft, or other causal messenger from that event could have arrived here by now. The phrase "by now" is essential. The particle horizon belongs to a particular observer at a particular cosmic time. As time passes, additional signals may enter the observer's past light cone, and the co-moving particle horizon can change. It summarizes all causal contact accumulated through the past. It is not an eternal fence fixed at one distance. It is also centered on the observer. An observer in another galaxy has a particle horizon around a different location. Their observable region overlaps with ours, but is not identical. They may receive signals from areas whose information has not reached Earth, while we may receive signals from areas still hidden from them. If that sounds as though every observer occupies the center of a sphere, it does not create many physical centers of the universe. The spheres describe access to information. A listener standing in a large field hears sounds arriving from around their own location, but that does not make the listener the center of the field. In cosmology, the causal structure is more complex, yet the basic warning remains: an observer-centered horizon is not a creation center. What, then, lies beyond our particle horizon? The honest answer is that we do not directly know. The standard cosmological model suggests that the large-scale patterns observed within our region continue beyond it, but that statement is an extrapolation. It is supported by the regularity of the accessible cosmos and by theories of its early development. It is not based on signals received from beyond the boundary. Regions outside the horizon may contain more galaxies, gas, dark matter, radiation, black holes, and perhaps structures unlike anything in the observable volume. Or conditions could differ on scales too large for us to sample. Since no information from those regions has reached us, direct observation cannot decide between every possible global extension. This is why the observable universe and the entire universe must never be treated as synonyms. The observable universe is the region connected to our past light cone. The entire universe means all of space-time, or all space on a chosen cosmic slice, including whatever may lie beyond present causal contact. The full universe may be vastly larger than the observable region. It may be spatially infinite. It may instead be finite, without possessing an ordinary edge, depending on its global geometry and topology. A finite space need not end at a boundary, any more than the two-dimensional surface of Earth ends at the edge of a map, although this analogy describes geometry rather than the actual number of spatial dimensions. Measurements can still tell us something. Observations of the cosmic microwave background and large-scale structure constrain spatial curvature. The observable region appears very close to geometrically flat on large scales. If the whole universe has strong curvature, its characteristic scale must therefore be large compared with the region we can inspect. But near flatness does not prove infinity. A small patch of a very large curved surface can appear flat, and a globally finite space can also possess flat local geometry under some topologies. Curvature measurements place limits on possibilities. They do not reveal the total extent. Scientists also search for signs of a compact cosmic topology. If space wraps around on scales small enough, light from one structure might reach us along different paths, producing repeated patterns or matched features in the cosmic microwave background. No confirmed pattern has established such a topology within the observable range. That absence constrains smaller possibilities but does not prove that space is infinite or simply connected. Inflationary models often predict that the region beyond our horizon is enormously larger than what we see. Inflation can explain why widely separated observable regions display similar large-scale conditions and why space appears close to flat. Yet inflation is itself a theoretical framework with multiple versions. It cannot provide a direct photograph of the unseen exterior. The particle horizon, therefore, creates a form of underdetermination. Different possible global universes can contain an observable region like ours and produce the same measurements inside our past light cone. If their differences occur only beyond causal reach, current observation cannot distinguish them. This does not make cosmology helpless. A theory may still be preferred because it explains accessible evidence more simply, connects with tested physics, or makes predictions that can be checked within the observable region. Scientific reasoning does not stop at what the eye sees. But confidence must reflect the distance between direct measurement and extrapolation. The horizon also changes the meaning of cosmic maps. A map of the observable universe does not show matter at one shared time. Nearby structures are mapped from relatively recent light, while remote structures are mapped from earlier epochs. The outermost regions in the map are not neighboring a present-day physical shell that we directly see. They are ancient events along the deepest accessible parts of our past light cone. Even the roughly 46 billion light-year radius is a present co-moving translation of that history. The radiation defining our deepest electromagnetic view was emitted when the proper separations were much smaller. The radius allows us to represent those co-moving locations on today's model slice, but it should not be mistaken for an image of their current states. There is also an important difference between being inside the particle horizon and being visible. A region may be causally connected in principle, while its signals are too faint, obscured, absorbed, or outside the sensitivity of present instruments. More fundamentally, the early universe itself was opaque to freely traveling light. Before a certain epoch, matter existed as a hot ionized plasma. Photons repeatedly scattered from charged particles instead of traveling across the cosmos in straight, uninterrupted paths. Those early regions can lie within our broader causal history, while remaining hidden from direct electromagnetic sight. The particle horizon is therefore the outer boundary of possible past causal contact, but it is not identical to the oldest surface we can photograph with light. Inside it lies another boundary set, not purely by geometry, but by the physical state of matter in the young universe. This distinction brings the investigation closer to the beginning, without allowing it to reach a literal beginning. Our telescopes can collect photons that have traveled for almost all cosmic history. When traced backward, however, those photons converge not on time zero, but on an epoch when the universe changed from opaque to transparent. The glow from that transition fills the entire sky. It is the cosmic microwave background, the oldest freely propagating electromagnetic light available to us. Yet even this famous background is often pictured too simply. It is not a rigid wall, not the outer edge of space, and not an infinitely thin photograph. It is a layer in time and distance, formed while transparency emerged over a finite interval. To understand why the oldest light is not the beginning, we must enter the hot cosmic fog from which that light escaped. Long before stars and galaxies existed, the universe was filled with a hot, dense mixture of radiation and matter. Temperatures were so high that ordinary neutral atoms could not remain assembled. Electrons moved freely among positively charged nuclei, creating an ionized plasma. Light existed everywhere in this early environment, but it could not travel freely across great distances. Photons repeatedly encountered free electrons and scattered. A photon might move briefly in one direction, strike an electron, and be redirected. The young universe was luminous, yet opaque, much like the interior of a dense fog or the glowing material inside a star. Calling it dark would therefore be misleading. The obstacle was not the absence of light. It was the absence of a clear path. Information carried by individual photons was continually mixed through repeated interactions, preventing an electromagnetic image of still earlier regions from traveling directly to us. As the universe expanded, it cooled. After roughly 380,000 years, conditions became cool enough for electrons and nuclei to combine into neutral atoms, especially hydrogen. This process is called recombination, although the name reflects historical terminology rather than electrons combining for a second time. The transition is commonly associated with a redshift near 1100. Redshift here describes how much cosmic expansion stretched the radiation after emission. It also gives astronomers a way to connect the observed microwave sky with the scale factor and temperature of the young universe. Converting that redshift into an age near 380,000 years depends on the cosmological model, but the resulting picture is supported by several linked measurements with high precision. With far fewer free electrons available, photons were no longer scattered constantly. The universe became transparent over a finite interval, and radiation began traveling across space much more freely. Those ancient photons have continued through the expanding cosmos for almost its entire observable history. Expansion stretched their wavelengths enormously. Radiation once associated with a temperature of thousands of degrees now arrives primarily as microwaves, with an average temperature only a few degrees above absolute zero. This relic glow is the cosmic microwave background, or CMB. The CMB surrounds us because every direction on our past light cone eventually reaches the epoch when the universe became transparent. It is not radiation coming from one central object. It is light arriving from a vast set of last scattering events distributed around our observable position. When cosmologists call this the surface of last scattering, the word surface can create the wrong image. It is not a solid shell floating at the edge of space. It is the collection of space-time locations from which the photons reaching us last scattered before traveling freely toward our detectors. An observer in another galaxy would see a different last scattering surface centered on that observer's location. Their photons would come from a different set of ancient events. Once again, the spherical appearance reflects the observer's past light cone, not a privileged center of the cosmos. The surface is also not infinitely thin. Recombination and photon decoupling did not occur everywhere at one mathematical instant. The probability that a photon would scatter for the last time rose and fell across a finite period as temperature, density, and ionization changed. Measurements of the CMB allow scientists to estimate this thickness with remarkable precision. One analysis by Borjana Hajiska and David Spergel constrained the co-moving thickness of the last scattering surface to roughly 19 megaparsecs. A megaparsec is about 3.26 million light-years, so the quoted co-moving thickness corresponds to tens of millions of light-years. That enormous distance does not mean recombination lasted tens of millions of years. Co-moving thickness translates the interval into present-scaled coordinates. The physical thickness at the time was smaller because the cosmic scale factor was much smaller. The number must therefore be presented with its distance definition attached. The precision itself carries an important lesson. Even the oldest electromagnetic image is not a perfect photograph of one instant. It is an observational layer formed across a distribution of last scattering times and locations. Different photons in the background ended their repeated interactions at slightly different stages. Tiny temperature and polarization variations across the CMB preserve information about density, motion, and conditions in the early plasma. These patterns later became connected to the growth of galaxies and large-scale structure. By studying them, cosmologists can test models of matter content, geometry, expansion, and primordial fluctuations. Yet this power should not blur the distinction between direct light and inference. The CMB photons directly reveal the last scattering era. Conditions before that era are reconstructed from the patterns those earlier processes left behind, combined with other physical evidence. For example, the relative abundance of light elements supports calculations of nuclear reactions during the first minutes of cosmic history. The distribution of later structures carries information about initial density variations. These are powerful observational consequences of earlier conditions, but they are not ordinary photographs taken before the universe became transparent. Other cosmic messengers could, in principle, reach us from earlier epochs. Neutrinos stopped interacting freely much earlier than photons, leaving a predicted cosmic neutrino background that remains extremely difficult to detect directly. Primordial gravitational waves, if they exist at detectable strengths, could also carry information from very early processes. Such possibilities extend the kinds of evidence available, but they do not abolish causal structure. Every messenger has an interaction history and must follow an allowed path to reach us. A new detector may look through an electromagnetic fog, yet it cannot receive information from outside the observer's causal past. Nor does the CMB show the Big Bang as a point of creation. It shows the universe at a later transition, hundreds of thousands of years after the earliest hot phase described by the model. The word "after" is important, because known physics becomes increasingly uncertain as calculations are pushed toward the earliest moments. The CMB is sometimes called the oldest light in the universe. More precisely, it is the oldest electromagnetic radiation that has traveled freely to us from the era of last scattering. Earlier photons existed, but their repeated interactions prevented them from carrying an uninterrupted image across cosmic history. If we tried to look farther using only electromagnetic radiation, we would not see through the plasma by building a larger optical telescope. More sensitivity could measure the CMB with greater detail, but the photons required for an earlier direct image did not free stream from those epochs to us. This makes the last scattering layer a practical electromagnetic horizon. It is a horizon created by the physical opacity of matter, nested inside the broader causal limits defined by space-time geometry. The particle horizon asks what could ever have influenced us since the beginning of the model. The last scattering boundary asks how far back freely traveling photons can show us directly. The two must not be confused. The particle horizon is the boundary of past causal contact. The CMB surface is the boundary of direct electromagnetic imaging of the early universe. Evidence for earlier epochs survives through indirect imprints and possible non-photon messengers. This nested structure reveals why stronger technology can improve cosmology without completing it. Better instruments can extract fainter polarization signals, map smaller variations, reduce noise, and test competing models. They can refine what the ancient layer tells us. They cannot turn an opaque plasma into a transparent window that existed when it did not. The limit is physical rather than merely practical. Still, it is not the final observational limit in the story. The early universe prevented old photons from traveling freely toward us, but the future expansion of the universe can prevent newly emitted photons from ever reaching us. At first, one might assume that time is always on the observer's side. If a region is not visible today, perhaps waiting long enough will allow its light to arrive. The particle horizon has grown through cosmic history, after all, and every additional year gives nearby signals more time to travel. But accelerated expansion changes that expectation. Under the Standard Model, some present events are separated from us in such a way that signals emitted now will never arrive, even if observers wait without limit. The CMB teaches that there are epochs we cannot photograph because the universe was once opaque. The next horizon teaches something more unsettling. There are present realities we may never observe because the future does not contain enough causal time to bring their information home. Waiting usually increases what an observer can know. Light from more distant events has additional time to arrive. Instruments collect longer records, and a growing archive reveals changes that were previously hidden. In a static universe of sufficient age, patience might seem capable of expanding observation without limit. Our universe does not appear to follow that simple future. Measurements indicate that its large-scale expansion is accelerating. Within the standard lambda cold-dark matter model, this acceleration is associated with dark energy behaving like a cosmological constant. If that behavior persists, the future contains a cosmological event horizon. The event horizon is defined by a question different from the particle horizon. The particle horizon asks which past signals have managed to reach us by today. The event horizon asks which signals emitted at a given time can ever reach us, even if the observer waits indefinitely. This boundary appears because light has only a limited amount of effective co-moving distance left to cross in an eternally accelerating expansion. Cosmic time may continue without end, yet the scale factor can grow so rapidly that the remaining distance a signal can cover in co-moving coordinates is finite. Cosmologists often express this remaining opportunity through conformal time, a coordinate that accounts for expansion when tracing light across co-moving space. Ordinary cosmic time may stretch infinitely far ahead, while the remaining conformal interval approaches a finite value. On a suitable space-time diagram, future light rays continue upward but reach only a limited range of co-moving locations. The mathematics captures a physical fact. Endless duration does not guarantee unlimited causal reach when the scale connecting distant regions grows quickly enough. This is why the event horizon cannot be understood by asking only how many years a photon travels. Its route must again be integrated through the changing geometry, this time from the present toward the entire assumed future of the cosmos. That statement can sound contradictory. If a photon travels forever at light speed, why can it not eventually cross any distance? The answer is that local travel continues while the large-scale separation changes. The photon always moves at c in its neighborhood, but the destination's cosmological distance can increase in such a way that the signal never completes the global journey. Imagine sending a radio message today toward an extremely distant co-moving galaxy. Locally, the radio waves depart Earth at light speed. Along every small part of their route, relativity works normally. But if the galaxy lies beyond the relevant event horizon, expansion prevents the message from ever reaching it. The signal continues, the future continues, and still the separation cannot be overcome. The same logic works in reverse. Light emitted now by a sufficiently distant source may never arrive here. This does not mean the source is invisible today. We may already be receiving photons it emitted billions of years ago, when conditions and separations were different. A visible galaxy can therefore possess a present that is permanently hidden from us. Its ancient image remains in our sky because old light entered a successful causal path. Its newly emitted light may lie on paths that asymptotically fail to reach our location. This is one of the clearest reasons the universe cannot be observed as it is now. The delay is not always temporary. For some regions under the standard future model, there is no later date at which their present information finally arrives. The missing signal is not merely late. It is excluded from our entire future causal history. The event horizon's present distance is often quoted as roughly 16 to 17 billion light-years in co-moving terms, depending on the precise parameters and definition used. This is much smaller than the roughly 46 billion light-year particle horizon radius. The difference is not an inconsistency. The particle horizon includes ancient signals received from a much larger region. The event horizon identifies where signals emitted now can still enter our future. One measures accumulated access from the past, the other measures remaining access through the future. The Hubble sphere is different from both. It marks the distance at which recession rate equals c at a chosen cosmic time. Its position may change, and photons can cross it. The event horizon is the deeper causal boundary. Under the assumed future expansion, signals from beyond it never reach us, no matter how the Hubble sphere evolves along the way. Even here, the wording must remain careful. An event horizon is defined using the entire future expansion history. We cannot directly observe the future to confirm that dark energy behaves forever like a cosmological constant. We infer the horizon by extending the best supported present model. If dark energy changes with time, decays, reverses acceleration, or behaves in some unexpected way, the future horizon could shift or might not exist in the same form. Present observations strongly support accelerated expansion, but they do not provide an empirical recording of eternity. The event horizon should therefore be presented as a robust consequence of persistent lambda-like acceleration, not as a model-independent certainty under every possible cosmology. The conditional language does not weaken the science. It states exactly where measurement ends and extrapolation begins. Under the standard model, crossing an event horizon is also not an event we watch happen at one sharp instant. We continue receiving older and increasingly redshifted light from distant galaxies. Their signals become stretched, dimmed, and delayed. The galaxies do not appear to strike a visible wall and vanish immediately. Instead, their accessible history becomes increasingly limited. Each later signal takes longer to reach us and arrives with greater redshift. Beyond some emission time, no new signal ever arrives. What remains in our data is an aging sequence drawn from the source's earlier past. This creates an unusual asymmetry. The galaxy may continue existing normally in its own local environment. Stars may form, civilizations could rise, and events may unfold. None of that requires physics to stop there. What ends is the possibility that information about those later events reaches us. Likewise, observers in that galaxy can lose access to our future. Each region continues within its own causal neighborhood, while communication between them becomes permanently impossible. Expansion divides one connected observational history into domains that can no longer exchange new information. Distance alone does not identify this fate. A currently distant object may be gravitationally bound within a structure and resist cosmic expansion locally. The Milky Way, nearby galaxies in the local group, and the eventual bound remnant of that group follow local gravitational dynamics rather than simply being pulled across a cosmological horizon. The event horizon matters across large unbound scales where the cosmic expansion dominates. Bound systems can remain together even while increasingly remote structures disappear from causal contact. This distinction also keeps expansion from being imagined as a force tearing apart every object. Persistent acceleration can isolate galaxy groups without necessarily stretching their stars, planets, or atoms. The loss is between distant regions, not inside every local structure. The title's promise now becomes sharper. We fail to observe a simultaneous universe for more than one reason. Distant light shows the past. Relativity denies a unique observer-independent global now. The particle horizon excludes regions whose signals have never reached us, and an event horizon can exclude new information forever. Technology can improve every signal that remains available. It can enlarge detectors, reduce noise, and discover new messengers. It cannot recover a photon that never enters our causal future. The emotional consequence is not simply that space is large. It is that parts of the visible cosmos are already represented only by histories whose later chapters may be inaccessible. We see the light of places with which the possibility of present communication has ended. Waiting will still reveal new events from many sources. Our past light cone continues to develop, and astronomy will keep gaining information. But waiting does not guarantee universal completion. Under acceleration, time can close windows as well as open them. Carry this process far enough into the future, and the night sky changes profoundly. Remote galaxies become more redshifted and fainter. Eventually, observers inside a gravitationally bound island may lose the observational evidence that now reveals cosmic expansion and the hot Big Bang. The event horizon does not merely hide distant presence. Over immense timescales, it can change what the universe appears to be and what its inhabitants are able to discover about its origin. Imagine astronomy in a future so distant that the familiar night sky has been transformed. The stars within the local gravitationally bound remnant still shine, although their populations and environments have changed. But beyond that local island, the great web of external galaxies is no longer available as it is today. Under a future dominated indefinitely by a cosmological constant, unbound galaxies continue to recede. Their light is stretched to longer wavelengths, their apparent brightness falls, and their newly emitted signals become unable to cross the event horizon. Over immense timescales, the observable extragalactic sky empties. The galaxies do not necessarily cease to exist when they disappear from view. Many continue their own local histories beyond our causal reach. What vanishes is the stream of information connecting their later events to observers in our region. Gravity preserves a local island. The Milky Way and Andromeda are expected to become part of a merged bound system, together with other matter that remains gravitationally attached to the local group. Cosmic expansion does not pull apart this remnant in the standard scenario. Instead, it isolates the remnant from increasingly distant, unbound structures. An observer living there could study local stars, planets, black holes, and the dynamics of the merged galaxy. But the observer's large-scale evidence would be radically poorer than ours. The distant galaxies that now reveal a broad relationship between redshift and distance would be absent from practical observation. Without those external galaxies, the expansion of the universe would be far harder to discover. Local stars are gravitationally bound and do not participate cleanly in the Hubble flow. A scientist restricted to one island might build an excellent theory of local gravity while finding little direct evidence that space on the largest scales had expanded for billions of years. The cosmic microwave background also changes. As the scale factor grows, its wavelengths stretch and its temperature falls. The background becomes colder, weaker, and shifted to increasingly long wavelengths. Eventually, detection faces more than the challenge of constructing a sensitive receiver. Radiation at extremely long wavelengths interacts with the environment of the future galaxy and may be blocked by surrounding plasma. The ancient afterglow that now covers the sky can become physically inaccessible to observers inside the island. This fading is gradual rather than a single universal deadline. Different galaxies and different classes of evidence disappear on different timescales. A figure such as 100 billion years can indicate the era when much of the external large-scale universe has redshifted beyond practical view in standard projections. But it should not be treated as an exact moment when all cosmological knowledge switches off. The projection is especially valuable because it turns an abstract horizon into an experiment in perspective. We usually ask what better telescopes will reveal. Here the question reverses. What happens when the same laws remove the targets themselves from possible measurement? The answer shows that observational limits are not always failures waiting for invention. Sometimes the available universe changes around the observer, narrowing the evidence faster than technology can compensate for its loss across the deepest reaches of cosmic time. The deeper point is that the evidence set changes with cosmic epoch. Today we can compare the microwave background, galaxy redshifts, supernova distances, elemental abundances, large-scale clustering, and many other observations. These independent lines support a coherent history in which the universe expanded from a hotter, denser state. Far future observers may inherit fewer of those lines. The primordial abundance of light elements could become difficult to recognize after generations of stellar processing alter local material. The structures available for study may reveal little of the larger distribution from which the local group formed. The background radiation may no longer be measurable. Those observers would not be less intelligent than we are. Their instruments could be extraordinarily advanced, their mathematics flawless, and their local experiments precise. Yet science can use only evidence that nature makes available. If the signals carrying cosmic history no longer enter their observable environment, brilliance cannot reconstruct every missing fact uniquely. They might reasonably infer that their isolated galaxy exists in an otherwise empty, static cosmos. They could search for expansion and fail to find the galaxies required to measure it. They could look for a universal thermal background and detect none. Their best evidence might support a picture that is locally accurate, but globally incomplete. The physical universe would still possess its history. Expansion would still have occurred. The hot early phase would still be part of the past. Dark energy could still dominate the large-scale dynamics. What changes is whether these facts remain empirically recoverable from inside the future island. This creates a disturbing symmetry with our own situation. We know that future observers may mistake an information-poor sky for the whole universe because our present model allows us to describe what has passed beyond their reach. But we cannot stand outside our own horizon to check whether our sky is missing equally decisive evidence about a larger reality. Perhaps our epoch gives us an unusually rich cosmological window. We can observe galaxies across many stages of development. We can measure expansion over long baselines. We can detect the CMB and compare its patterns with later structures. The universe currently carries several readable records of its evolution. That does not make our location spatially privileged or our knowledge complete. It means the timing of observation matters. Cosmology is possible in its present form, partly because the necessary signals are arriving during our epoch. The idea challenges a common assumption about scientific progress. We often imagine that later civilizations must know more because they inherit earlier discoveries and possess better technology. In many fields, that may be true. In cosmology, however, the primary evidence itself can fade, redshift, or cross beyond causal reach. Knowledge can be preserved in records if those records survive and remain trusted. A future archive could contain our maps and measurements, but an inherited statement is not the same as independently available natural evidence. Without access to the original signals, future scientists may be unable to repeat the observations that established the cosmological model. If records are lost, corrupted, or dismissed, nature may no longer offer the same path back to the conclusion. The universe can become observationally simpler while remaining physically vast and historically complex. This is why the phrase "end of cosmology" does not mean that curiosity, physics, or astronomy literally stops. Future observers can continue studying their local system. It means that evidence for the large-scale expanding universe and its hot origin may become unavailable, leaving major features of cosmic history extraordinarily difficult or impossible to recover. The scenario remains model-dependent. It assumes that accelerated expansion persists, that dark energy behaves broadly like a cosmological constant, and that no unexpected future messenger restores the missing information. Exact timescales depend on astrophysical environments, as well as cosmological parameters. Still, the causal principle behind it is secure. Observers do not discover reality from nowhere. They infer it from signals, patterns, experiments, and records available within their past light cones. Change that accessible evidence, and the conclusions they can justify may change as well. This does not reduce science to opinion. The future observer's local measurements can be perfectly objective. The limitation is that multiple global histories may become compatible with the same reduced evidence. Without distant galaxies or an observable CMB, the data may no longer select our current cosmological history uniquely. Our present success, therefore, carries a responsibility for precision. We should distinguish direct observations from inferences, preserve measurements, and state which conclusions depend on a model. Doing so recognizes that our unusually informative sky is not guaranteed forever. It also prevents triumphalism. We have learned the age, composition, geometry, and evolution of the observable universe with astonishing accuracy. Yet all of that knowledge comes from one causal region during one cosmic era. The quality of the reconstruction does not remove the boundaries around its evidence. The Far Future Island reveals the central lesson in emotional form. A civilization can inhabit the same universe, obey the same laws, and possess advanced instruments, yet encounter a sky that conceals its own origin. Reality has not become smaller. The observable record has. This leads back to the question facing us now. We have more evidence than those projected future observers, but we still see only one past light cone. Can our models use the regularities inside it to determine what exists beyond it? Or could different unseen universes produce the same observable history? Before giving the final answer to the title, we must identify exactly what inference can achieve, where its confidence comes from, and where even the strongest model reaches an unavoidable boundary. The fact that observation has limits does not mean cosmology knows only what a telescope photographs directly. Science is powerful, precisely because it can connect different measurements through physical laws and test whether one explanation accounts for all of them. The cosmic microwave background supplies a map of conditions near the era of last scattering. Galaxy surveys show how matter later gathered into filaments, clusters, and voids. Characteristic patterns known as baryon acoustic oscillations provide a cosmic distance scale. Exploding stars trace the recent expansion history. Gravitational lensing reveals how mass bends light, including matter that does not shine. Each probe has its own uncertainties. Their value increases when they converge. A cosmological model cannot fit only one observation while ignoring the rest. It must connect early radiation, later structure, distance, expansion, composition, and age within one consistent framework. The lambda cold dark matter model succeeds because a relatively small set of ingredients explains an enormous range of accessible evidence. That does not make every detail settled. Tensions, parameter disagreements, and unexplained phenomena remain. But the framework is not a story invented to fill unseen space. It is constrained by repeated comparisons between prediction and measurement. This allows cosmologists to infer more than direct images alone contain. From the CMB's statistical patterns, they estimate matter density and spatial geometry. From redshifts and standardizable explosions, they reconstruct expansion. From the distribution of galaxies, they test the growth of structure. Inference becomes reliable when independent paths lead to compatible results. One principle makes this reconstruction possible on the largest scales. The cosmological principle states that, when viewed over sufficiently large regions, the universe is statistically homogeneous and isotropic. Homogeneous means that no large region is fundamentally unique in its average properties. Isotropic means that the large-scale pattern does not select a preferred direction. The principle does not claim that every location looks identical. The universe clearly contains stars, galaxies, clusters, and vast voids. It is a statistical statement that these variations form a broadly similar large-scale distribution when averaged over enough volume. Observations support this picture strongly within the accessible cosmos. The CMB is remarkably uniform across the sky, with small fluctuations that carry the seeds of later structure. Galaxy surveys show increasing statistical uniformity on large scales. Multiple measurements can be interpreted within the same expanding geometry. There are reported anomalies and debated large-scale alignments. Scientists continue testing whether these reflect new physics, local structure, observational systematics, or statistical chance? Such questions deserve careful study, but they do not currently justify presenting the cosmological principle as overturned. At the same time, the principle cannot be directly tested everywhere. All available data come from events inside our past light cone. When cosmologists extend large-scale homogeneity beyond the particle horizon, they are applying a successful principle outside the region where signals can verify it. That extrapolation may be reasonable. A theory does not become useless at the exact boundary of a telescope's view. Physical laws tested in one laboratory are applied elsewhere, and astronomical models routinely predict phenomena before they are observed. The important point is to label the step correctly. Inside the observable region, homogeneity and isotropy are evidence-supported approximations. Beyond it, their continuation is a model-based inference. No observation from the exterior can currently confirm or contradict the extension. This creates global underdetermination. Imagine several possible universes that are identical throughout our entire past light cone but differ outside it. One may continue indefinitely, with similar large-scale conditions. Another may possess a finite topology. A third may change far beyond the accessible region. If every observable signal is identical, no experiment available here can presently distinguish them. The possibilities are not automatically equally plausible. A simpler extension consistent with tested physics may be preferred over an elaborate alternative invented without evidence. Theoretical consistency and explanatory power matter, but preference is not the same as direct confirmation. Spatial curvature illustrates the distinction. Measurements show that the observable universe is very close to flat on large scales. This constrains strongly curved models with small characteristic sizes. It does not establish that the total universe is infinite. A finite region of a much larger curved space can appear nearly flat, and some finite global topologies can be locally flat. Searches for repeating patterns can also constrain compact shapes. If light had traveled around a small finite universe, the same structures might appear in multiple directions or produce matched patterns in the CMB. The absence of confirmed repetitions rules out some small topologies, not every finite possibility. We therefore know a minimum scale more readily than a total scale. The observable patch must fit the evidence, and any global model must contain a region consistent with it. But the unseen remainder can remain ambiguous when its differences produce no accessible signal. The same boundary applies to the future. Present measurements indicate accelerated expansion, and the cosmological constant model predicts an event horizon. Yet the exact eternal behavior of dark energy cannot be watched in advance. The horizon is a strong conditional prediction, not a direct measurement of endless future time. Separating levels of knowledge avoids two opposite errors. The first is false certainty, claiming that the model has photographed or proven the whole universe. The second is empty skepticism, claiming that nothing can be known because every observation is incomplete. A more accurate position lies between them. We directly measure arriving signals. We infer causes and parameters through models tested against many independent observations. We extrapolate beyond the observed region when a successful framework gives reason to do so. And we acknowledge philosophical possibilities that may remain scientifically undecidable if they produce no different evidence. These categories are not signs of weakness. They are how science keeps confidence proportional to support. An observation, a strong inference, a model-dependent conclusion, a speculative hypothesis, and a philosophical reflection should not be narrated as though they carry equal weight. They also show why confidence can remain strong without becoming absolute certainty. With those boundaries in place, the answer to the documentary's question can finally be stated without exaggeration. We know far more than the small portion of reality directly imaged at one wavelength. We can reconstruct an ancient cosmic history with extraordinary precision. We can test geometry, expansion, and composition across billions of years. But no model turns an unreceived signal into an observation. No successful extrapolation places an observer outside their own causal structure. Different global realities may remain compatible with every measurement available inside one cosmic patch. The final limit is therefore not ignorance of everything. It is the impossibility of converting one observer's causally assembled archive into a complete, simultaneous, directly verified portrait of the whole universe. We now have every piece required for the answer: delayed light, relative simultaneity, the past light cone, changing cosmic distances, particle and event horizons, early opacity, and model-dependent inference. Together, they reveal what the title's impossible observation actually is. The impossible observation is not a sharper image waiting for a more advanced telescope. It is not hidden behind insufficient magnification, weak sensors, or a lack of patience. It is a complete and simultaneous view of the entire universe, delivered to one observer. No observer can possess that view, because observation begins with causal contact. Every measurement is made from signals arriving at one place and one moment. Nearby signals reveal the recent past. Distant signals reveal deeper history. Together, they form a past light cone, not a map of everything at one universal present. The light is real. The galaxies are real. The events recorded in their radiation genuinely occurred. The limitation is not that astronomy shows an illusion. It is that the received events belong to different times and cannot be combined into one directly witnessed cosmic now. Relativity makes the desired snapshot even more difficult to define. Across great distances, simultaneity is not independent of an observer's motion or chosen frame. Cosmologists can define cosmic time within a large-scale expanding model and construct surfaces representing one stage of cosmic evolution. Those surfaces are scientifically useful, but they are theoretical slices. No camera receives every point on one such slice at once. Even after a cosmic time convention is chosen, the signals remain restricted by geometry. The finite age of the universe and its expansion history create a particle horizon. Regions beyond it have never sent information that could reach us by today. Their possible existence can be inferred or modeled, but not directly verified from signals that have not arrived. Inside that broad causal boundary, electromagnetic observation meets the opacity of the young universe. The cosmic microwave background shows the era when photons began traveling freely, not the beginning itself. Its last scattering surface is a finite layer, and earlier conditions are reconstructed from imprints, physical theory, and other possible messengers. Expansion also points toward a future limit. If accelerated expansion continues as the Standard Model predicts, a cosmological event horizon excludes some newly emitted signals forever. We can see ancient light from galaxies whose present events may never enter our future. For those regions, the missing now is not only delayed, it is permanently inaccessible to us. These limits do not disappear if humanity moves elsewhere. A spacecraft, a colony, or an observer in another galaxy would gain a different past light cone. Some previously hidden events could become visible, while others would be lost. Nor could a civilization distribute telescopes everywhere and instantly combine their records. Every record must travel to a receiver before comparison. The combined information would again arrive through signals and would again describe the past relative to the event where it was assembled. There is no balcony beyond space-time from which the whole cosmos can be watched. The imagined God's eye photograph is not one of the observables available to an inhabitant of the universe. This is the scientific climax of the title. It is impossible to observe the universe as it really is, if that phrase means seeing every region at one shared present in one complete image. It is the causal and relativistic structure of observation itself. But that answer does not leave us knowing nothing. From one finite archive, cosmology has reconstructed a history extending billions of years. The microwave sky, galaxy distributions, stellar light, elemental abundances, gravitational lensing, and cosmic expansion all constrain one another. Independent evidence turns fragments of different times into a coherent physical account. We can estimate the age of the universe, trace the growth of structure, measure its large-scale geometry, and explain why the observable radius is far greater than a static calculation suggests. We can identify where direct observation ends and where model-dependent inference begins. Reliable knowledge does not require an impossible view from nowhere. It requires testable relationships among the signals available somewhere. Our models earn confidence by surviving comparisons with evidence, not by pretending to remove the observer from space-time. We do not know the total size of the universe. We do not know whether space is globally finite or infinite. We cannot directly test the cosmological principle beyond our horizon, and we cannot observe the eternal future to confirm exactly how dark energy will behave. They mark the point where the evidence stops distinguishing among possibilities. A disciplined answer allows the known universe to remain astonishing without turning the unseen into fact. The human reframe is therefore neither despair nor triumph. We are not spectators standing outside reality, receiving a finished picture. We are physical participants inside it, gathering signals that have crossed different distances, survived different environments, and arrived during one particular cosmic era. Our location is not the center of creation. It is the center of our causal view, as every observer's location must be. Our time is not the universal present. It is the event at which this collection of ancient messages happens to meet. That makes the sky more meaningful, not less. Each photon is evidence that some event succeeded in reaching us across an evolving cosmos. Every star is shown through a delay. Every galaxy contributes a surviving page from a history whose later pages may still be traveling or may never arrive. Return, then, to the clear night with which the journey began. The moon, the stars, and the unseen galaxies still appear together above you. Nothing about their light has become unreal. What has changed is the meaning of together. They share one sky because their signals reach one observer now. They do not share one moment at their sources. The darkness above is layered with seconds, years, millennia, and billions of years, all arriving at the same small location. We can never step outside that structure and photograph the entire universe in its present state. We can only receive its histories, compare them, test them, and build the most faithful account the evidence allows. The universe does not present itself as one completed scene. It arrives as an archive, one signal at a time.